Welcome to Module 7. We're here in the last third of the course, and the emphasis is really going to be on biochemistry, starting with how we understand what organic molecules look like. We're going to bridge the gap between Lewis structures, which we've looked at in kind of a quick way, but that really emphasizes how atoms bond to one another and how when that bonding happens, we draw a little picture of how they bond. In biochemistry, molecules tend to be rather large, so we need some really clear representations of how we can show those, as well as on a larger molecule, how to pick out the most important parts of that molecule to get some feeling of understanding about what that molecule will do. And I will say that as far as looking at a molecule and understanding perfectly what it can do, that is not always possible. I mean, that is often at the cutting edge, and that isn't really a realistic goal for the course and definitely not something you should worry about. But when we look at an organic molecule, we can definitely understand a few things such as whether it's likely to be soluble, where certain functionality might happen, and how it might match other biochemical targets. But to begin with, we're going to look at carbon and how it arranges to be the backbone of life and how we can understand these schematics a little bit better. Introducing organic chemistry will be all about carbon. Carbon is the backbone of biological molecules and biological systems, and understanding how carbon leads to this is really an important part of understanding organic and biochemistry. And if we look at these organic molecules, what do they have in common? And there's a lot of things they have in common, but if we examine these, what we'll see is that for the most part, the structure of these molecules are all determined by carbon. They all contain carbon, and it's true that they all contain oxygen and things as well, but let's study the pictures of these for just a minute and notice that the bulk of the molecule, the structural significance of the molecule, is mostly determined by carbon, with a little bit of oxygen worked in there as well. Carbon is what determines the size, the structure for nearly all organic molecules. And so why is this the case? Why is carbon so special? And go ahead and pause here for a second and review a couple of questions. How many valence electrons does carbon have? Remember that atoms like to get to 8 valence electrons for bonded systems. And because of that number of valence electrons, and you can use a periodic table for this, you should, but based on the valence electrons carbon has, how many bonds can carbon make? Go ahead and pause here and see if you can answer those. All right, hopefully you were able to determine an answer here. Carbon forms 4 covalent bonds, and this is a number that really should be synonymous with carbon. You don't need to memorize it because you can use the periodic table to explain and get to why 4 is the number, but it is just one number and I think is one that you should really associate with carbon. And because it forms 4 covalent bonds from its 4 valence electrons, right? 4 valence electrons, it wants 4 more electrons. Those are the 4 covalent bonds. It makes a lot of bonds, and because of this, it makes a big variety of shapes, branching, chains, rings. This is why carbon determines the bulk of a molecule. And so let's look at hydrocarbons. So this is when they only contain hydrogen and carbon. And looking at these is a great lesson about hydrogen as well, because remember that hydrogen forms only one bond. And because hydrogen forms only one bond, it sort of caps things off, right? Carbon always wants to form 4 bonds. And if you only really want the molecule to go in one direction, well, you can just cap off those bonds with hydrogens. That's really the way I think is good to look at it. When we look at hydrocarbons, let's say it's just 2 carbons bonded to each other with hydrogens everywhere else. This we call an alkane. So it is a carbon and hydrogen containing molecule. That's all it contains. And there's nothing other than single bonds. And this is this C2H6 here. And what's really important to know about a single bond is that it rotates freely. They always rotate freely, but this is the bond that determines the structure and is what would be impactful if it didn't rotate freely. In contrast, double bonds and triple bonds, they are not allowed to rotate because of the structure of these double and triple bonds. And this determines a lot of things biochemically, but for the time being and for this course, really just knowing that single bonds are allowed to spin, whereas double and triple bonds cannot. And what this really significantly means for the middle picture here, our alkene, our C2H4, is that those hydrogens are kind of locked in place, and this is a flat molecule that really isn't allowed to rotate and spin. Strong and linear for triple bonded alkynes, cannot rotate. And another thing to notice is that the more bonding we have between the carbons, the fewer hydrogens we need. So a lot of times we can determine if there's a double or a triple bond present just from the number of hydrogens. For example, if I say C2H6, I can draw the top molecule and conclude that it must be a single bond because all the other carbon bonds are satisfied. C2H4, we know there has to be a double bond to satisfy carbon's four bonded needs. And the bottom, C2H2, we would know it's a triple bond, again, to make sure that carbon has four bonds for all the carbons. Carbon wanting four bonds is just nearly universal and is a number that you should keep in mind. The bond type affects the shape, it affects the reactivity, and because biological molecules are created with so few different types of atoms, it's the way that they're connected that determines so much. When we're looking at a hydrocarbon, or really anything with carbons, it's important to know that the number of carbons determines the size, and therefore we want to describe this just a little bit. And so to do this, we use prefixes. So the number of carbons that are involved in each of these molecules determines what the name of it is. And for just a hydrocarbon with no double bonds, we call this an alkane. And this is two examples of alkanes, right? It's just hydrogen and carbon, all single bonds. Methane in the top is just one carbon, and with only one carbon, we call that methane, prefix meth, and then alkane ends in ane. Propane, that is three carbons, and so the prefix prop is what goes with three carbons, and it ends up being propane. These prefixes are going to come up again and again when we describe molecules, and so I present them here just to take note of. I'll include them on the equation sheet for the course as well, so you don't need to memorize them, but just know that these words are really important in organic chemistry for describing the amount of carbon that's present on a molecule, right? The prefix describes the size, the suffix describes what class of molecule it is. In this case, alkane, meaning only hydrogen and carbon with no double bonds. The suffixes for alkenes, meaning one double bond, or alkynes, Y-N-E is pronounced "-ine", alkyne, for one triple bond, they now have different suffixes. But note that the amount of carbons are still determined based on those same prefixes we've seen before. And so here, we had these three molecules we looked at before. Based on this chart and this naming system, go ahead and pause here and see if you can name these molecules. Naming's not going to be a huge part of this chemistry course. That said, knowing these very common prefixes and how they can relate to very specific formulas unambiguously is really important to recognize in chemistry and why we use nomenclature. Okay, so were you able to come up with the names of these molecules? They are ethane, two carbons, and it's an alkane. Then we have ethene, it's two carbons, and it has a double bond. It's an alkene. And finally, ethyne. This one's also known as acetylene, so that's like, blowtorch molecule. Maybe you've heard of that. A lot of molecules have different names, but following this convention, ethyne describes it just fine, and that is the name for this one as well.